Hello, I hope you're well. So we continue with lecture B. All right, so just a quick reminder of what we did um, last time, because we will need these properties for today's lecture, which is a little bit harder than, of course, the last one. So you saw last time that if we are given a square matrix and asked to compute the determinant, you could do so by expanding along the first row. And if I want, I could also do my second row, a third row, a fourth row. And if you remember the formula for expanding along any row, let's call row I, was given by this formula, right? And it's really important that you go over this formula and understand how to use it before next week's test. And just to remind you, the m's here are the minor elements corresponding to the I and jth element of the matrix. The Cij's are the cofactors. And then we establish these six properties of determinants. Now I want to go to, so now that we know how to calculate determinants, and now that we understand from lecture A that an inverse of a matrix can only exist if the determinant is not zero, how do we actually calculate the inverse? And here's how we do it. So we need to know two things. We need to know the general formula, and we also need to know a simple proof. Someone gives you an n by n matrix, assuming the determinant is not zero. The inverse of this matrix is found by 1 divided by the determinant, which is a scalar, so you can actually do this thing here, multiplied by something called the adjoint matrix. So again, 1 divided by the determinant of that matrix up there times the adjoint matrix. And the adjoint matrix is given by this thing right here. At first glance, you're probably going to panic because it's a lot of symbols coming at you. But there's a certain method to this madness. Remember, the first element is 1, 1, next will be 1, 2, 1, 3, 1, n, and so forth. So, the same way, if you remember last previous lecture's discussion, you remember that if you did the Laplace expansion by some row, you would have to figure out whether you start with a plus or a minus. And the way we did this was by realizing that anytime the subscripts here, this is if this element was 1, 1, first row, first column, 1, 1 adds up to 2, 2 is an even number, it would be a plus. So all even numbered locations when you add the subscripts are plus, others are minuses. So this tells you that minus 1 to the power 1 plus 1 is an even number, it'll be a plus. And then if you and what the H1 matrix says is remembering the sign that you would have used for determining expand or finding determinants. So that's your minus 1 to the power 1 plus 1. Instead of x 1 1, put the corresponding minor element. Next would then be minus 1 to the power 1 plus 2, right? First row, second column, into m1 2, and so forth and so forth and so forth. It's also extremely important that you notice that there's a transpose here. Waterloo kids, I'm sorry, I'm not going to use a T. So here's the thing right here. But then, good news. Instead of trying to memorize this horrible form, you remember last time we said, in fact, I'll go back one slide over here. We said the cofactor is minus 1 to the power I plus j into the minor element. So these things are nothing but the cofactors. With that, you get a beautiful expression. The adjoint matrix is the cofactor for element 1, 1, cofactor 1, 2, and so forth, just like the original matrix, except the difference now is that you now have a transpose here. Excuse me. Let's now use this to find the inverse of a 2 by 2 matrix. Okay? So you really want to follow this discussion uh, closely because we have to use this kind of apparatus in a few minutes for Kramer's rule. Here's a 2 by 2 matrix. I'm going to calculate the determinant by the first expanding along the first row. You should be able to associate, you should be able to realize that x22 is the minor element corresponding to 1 x11, right? And then you should realize you should be able to write these expressions down in terms of minors and cofactors. And we're going to assume this entire expression is not equal to 0. The A-joint matrix is, of course, the matrix of cofactors transposed. The first so take element x11. Its cofactor is the minor element, which of course was minus 1 to the power 1 plus 1 plus into what was left over x22. So I'm not going to explain this any, well, maybe just one more. Well, fine. X12. You know that if the first was a plus, next one should be a minus. That's exactly what you see here. Minus 1 to the power 3 will give you a minus. Now what you want to do is you want to put the minor element corresponding to x12, which of course is x21. That's exactly what you see here. So these are all the cofactors. Transpose. So we simplify, as in like the signs. Now carry out the transpose. Now use the formula. So this is the adjoint matrix. Here's the now the inverse of the matrix X. 1 divided by determinant times the adjoint. 1 divided by determinant times the adjoint. Pass this algebra through, and here's a nasty animal that gives you the inverse of a 2 by 2 matrix. I'm going to check if this calculus is right on the next slide. You are going to find out an expression for a 3 by 3 matrix's inverse. Do it. To find out, to confirm that our answer was right, we remind ourselves that the inverse matrix is defined as something that when you multiply by the original matrix, it gives you the inverse matrix. Sorry, not the inverse matrix, the identity matrix. Original matrix, what we claim is the inverse, carry out the whole operation, and voila, you now have the identity matrix. So it is in fact correct. Here's how you find the inverse matrix using in Wolfram. Simple. It's the inverse of type the equation out of the matrix. Some properties of inverses, very important, especially for econometrics. Throughout, I'm going to assume that it's invertible, blah, blah, blah. If X is a symmetric matrix, then the inverse matrix is also going to be symmetric. The determinant of the inverse is the inverse of the determinant. Inverse of the inverse gives the original matrix. Transpose of the inverse is the inverse of the transpose. This is, again, I highlight this in red because people tend to forget this in econometrics. And you know what happens when you forget things in econometrics. That's right. So you remember that you do not want to say x inverse multiply y inverse. What you want to do is you want to flip the elements, right? So the inverse of xy is the inverse of y times the inverse of x. And then, of course, you can see this rule in action when you do a 3 matrix inverse. All right. Now we do Kramer's rule. This is extremely important because you'll see why it makes your life easy when things get more and more complicated as time goes by. We want to solve a linear system of linear equations time and time again in economics. Think of the Kuhn model, a demand supply model, macro models. There are countless models which consist of a system of linear equations. And as we have seen, these can be written in terms of a matrix A, square matrix, times quote unquote a vector or a matrix of k variables is equal to a vector or a matrix of k constants. If someone ever asks you to find x, one way to do this would be brute force. Right? Brute force is what you would do if you're living in the Stone Ages. You would have to go out, kill dinosaurs and God knows what, for food. Brute force. Times have changed, right? We don't need to go hunt bulls, buffaloes and dinosaurs anymore. So let's use brains. Brain says rather than using brawn and calculating x by having to take the inverse, which you just saw is not very easy, you could try to use a faster technique called the Kramer's rule, which comes next. And incidentally, knowing whether so notice that you cannot find a solution for x unless the determinant of a exists, right? Not 0. So sometimes, as you're about to see, having to say that the determinant of the square matrix A is not 0 gives you some restrictions on parameters for such a system to have a solution. So, for example, you may remember game theory and you may remember Kuno reaction curves, but you should remember that if they have to cross in a certain way, one has to be steeper than the other. If that flips so that the other is steeper than the first one, you're not going to have a solution. Instead of converging to a solution, you'll diverge away. So those restrictions of those parameters, what must be true with the alphas, betas, gammas, A, B, C, D, and so forth, to guarantee a solution, is given by the existence of the determinant, as I'll show you in a few minutes. Let's derive Kramer's rule. And just in case you're lost what which Kramer is definitely not the one from Seinfeld. Kramer's rule. We want to solve this system of equations. Ax is equal to b. Here's the matrix A. X equal to b. Had I not had Kramer's rule, I would have found x by inverting the A matrix, multiplying by b. So inverting A matrix times the b. But the inverse of this A matrix is, of course, 1 divided by determinant times the adjoint. That's exactly what we see here. And a few seconds ago, we saw that here's 1 over determinant. We saw the adjoint matrix was a transpose of the cofactors matrix. I have now done the transposing for you. See, the C12 comes down here. Right? So this has been transposed, and now this is the correct expression. And now what I do is I carry out the multiplication. So I'm going to multiply this matrix with that vector. So this will become B1 times C11 plus B2 times C21. That's exactly what you see here. So I've multiplied this matrix with the vector, and here's what you see. Now, x1, x2, the vector is equal to this. If I want to pull out just x1, which I'm now going to do, I'm going to pull out the first row of this matrix. So 1 divided by 1 over the determinant, multiply the first row, is your x1, and here's your x2. Now, you should get some coffee, because things are going to get nasty. Let's take a look at x1. Before I do so, let's jolt our memory. Do you remember how in the previous lecture we showed you the Laplace expansion? So here's a determinant using Laplace's expansion method by the first row. Okay. Remind yourself that A22 is nothing but the minor element corresponding to 1, 1. A21 is the minor element compared for element A12. And of course, you don't have to say M11 anymore. You can say plus C11. You don't have to say minus M12 anymore. You can say plus C12. Those are cofactors. So for your convenience, I've listed these things over here. What's C1, C12, etc., by elements. You'll see why these are useful. Now come back to this. 2 seconds ago, you said x1 is equal to 1 divided by determinant times some expression. If you look at this expression in red, compared to that expression over here, kind of looks like the same. It looks like you're trying to take a determinant of something. In fact, it becomes even more obvious when you compare this red expression, right, BC11 plus B2C21, with this expression. This is clearly the determinant of a matrix, this one right here. This looks like it could be the determinant of a matrix, but which one though? So I imagine that is this matrix. And you want to be now super careful. This red expression, the first line, would be the determinant of this matrix only if we carried out the expansion by the first row. Because you can see that if I did by the first row, I would do B1 times C11, right? And then I would do minus B2 times minus C21, which will then give you plus B2C21. So this quote-unquote determinant is of that matrix, and I had to write it this way to get that expression right here, because I'm expanding by the first row over here. But I remind myself that in the previous lecture, the determinant of a matrix is the same as the determinant of its transpose. So this determinant upstairs should be the same as this determinant down here. I've simply transposed the matrix inside. And now what you notice is something beautiful. You've got to give Kramer some credit. If you want to find the answer for x1, take the original matrix A and replace the first column of matrix A with the vector B. So once again, go back. This is your vector B. This is your matrix A. Kramer tells you that if you want to find the answer for x1, take the original matrix A, get rid of the first column because you're solving with the first x, and replace it with a vector b. And then take the determinant of this creature, divide by the determinant of the original matrix A, and then you're done. The next slide is for x2, but now things get even more subtle. Once again, x2, two slides back, we saw this expression. Again, if you compare this red expression with down here, it looks suspiciously, like a determinant, right? But of what? Now, if you really want to know how to study for grad school, here's how I would have done it. I would have said, wait a second, why don't I do the same thing I did in the previous slide? I'll write down, put B1 over here, and I'll put the B2 over here. And I urge you to try the same thing. What if you did put the B1 down here and you put the B2 over here? If you did this and you carried the determinant, you wouldn't get this expression. So the only way to get this expression is something along the following lines, right? You can do it this way. You can put B1, B2 in the second row and over here. Notice that if I take the determinant, I would be right because I would have to take, if I expand by the second row, it'll be minus B1 into minus C12, which is plus B1 C12, plus B2 into C22, which is exactly C here. So if you wrote it this way, and again you pulled out your one of your ace cards and said, look, the determinant of a matrix the same as the determinant of its transpose, you would then do this. Right? I've just transposed the matrix inside. And now what you want to do is you realize that what you have done is C22, maybe I forgot to mention this in the previous slide, sorry. Oops, my bad, sorry guys. How did I go from here to here? Notice that minus C21 was element minus A12, right? Sorry, C21 is minus A12. Therefore, minus C21 is plus A12. See, right here. C11 is A22. That's how I put A22 over there. The same way, C22 is, of course, A11. So I put A11 right here. C12 is minus A21. Minus A21 minus gives you plus A21. And brilliant. If you want to solve for the second x variable, take the A matrix and replace the second column by the vector P. Take the determinant, divide the determinant of the original matrix A, and then you're done. I think that's pretty cool. Wouldn't be a bad test question. All right, so in general, if you're solving this massive system like this, you want to solve for a sum baby xi, which could be 1 through n. Take the matrix A, replace the ith column by the vector P, take the determinant, divide the determinant of the original matrix A, and then you're done. And by the way, you'll be expected to use Kramer's rule definitely for anything up to 4x4 matrices. Let's use Kramer's rule for a simple macro model. You can imagine this is the macro model for North Korea. North Korea is a hermit kingdom. It does not trade. No imports, no exports, no nothing. Except for the great leader. So you'll notice that this is a bit unusual model. GDP is equal to consumption, investment plus government spending, but there's no net exports. I'm a hermit kingdom. I don't, it's like almost like Bhutan almost as well, right? No, you're just closed. But this is a tricky model. Your GDP-Y is equal to consumption, but your investment is always fixed. It's autonomous, I bar, and your G is always fixed. So every year, the great beloved leader of North Korea will always spend the same amount on government spending. Think of large buildings and statues. Investment, I don't know, think of cigars. But the consumption function is a Keynesian consumption function. If you remember from undergrad, there's a big difference between a Keynesian consumption function and a Friedman lifetime income hypothesis consumption function. In the Keynesian consumption function, your consumption depends on disposable income in a linear fashion. It has to be linear because if you ever read Keynes's great works, you will notice he says average propensity to consumption goes down as income goes up, and marginal propensity to consume is a number between 0 and 1. And the only way this can actually happen is if you have a linear function. So consumption, intercept, plus marginal propensity to consume, disposable income. We're being nice here. I'm actually telling you what the alphas and beta should be. Alpha should be bigger than 0, beta should be between 0 and 1. But on the exam, you will have to derive these conditions, and I'll show you how. Taxes. Taxes are proportional to GDP in a linear function. Here's some parameter gamma, which you're told is bigger than 0, and a delta, which is a number between 0 and 1. So you can write this closed economy system in this matrix form. And now somebody wants to tells you to use Cramer's rule to solve for GDP, consumption, and taxes. Well, here's the form, the AX is equal to B form. You know that you have to take ultimately the determinant of this matrix. And also, you remember what I said to you earlier, taking the determinant of this matrix gives you conditions or parameters for the solution to exist. If I take this matrix, expand by the first row, you get this, I think. And now notice that this number as well. So you have to ask yourself under what circumstances this number will not be equal to 0. So you can easily put some conditions on the betas and deltas on that this expression should not be 0. And then if you gave me one assumption, let's say a delta, right? You told me let's say delta was positive, I could deduce in 5 seconds that beta should be a number between 0 and 1, right? So a solution will exist as long as, for the time being, this expression is not 0. Assuming delta was positive, you can deduce that beta should be a number between 0 and 1. Other restrictions can also probably follow, so I'll leave that to you as an exercise. But here's what you do, right? So for GDP, since it's the first variable, replace the first column of matrix A by the vector B, right? Take the determinant. Here's the determinant of A matrix. For the second X variable, consumption, replace the second row and then you take determinants of this one, divide by this thing, and taxes are the third variable, so you would replace the third column of the A matrix by the vector B, and then carry on, right? So I need you to go and simplify these things and get closed form, closed expressions for GDP, consumption, and taxes. This is going to be painful. It's really important now to remember there's a difference between leading principal minors and simply principal minors. Leading principal minors means the following. What you want to do is, the easiest way to remember this is if you're given, let's say, a 3 by 3 matrix, you could consider the first 1 by 1 matrix. The determinant of that one would be the first order leading principal minor. Then I could take from going from 1 by 1, I could go to 2 by 2. The determinant of this 2 by 2 then gives you the second order leading principal minor. And I could keep going, so they're getting bigger. See, 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5 by 5. As I keep going like this, I keep getting leading principal minors. So you will have exactly, if you have an n by n matrix, you'll have exactly n leading principal minors. But let's now start to read. Let's use a different way of saying this. This is an exercise in notation and mathematics and how to read math. According to Martin Osborne, there are k is a number that goes from 1 through n. The leading principal minors of this matrix excuse me, are the determinants of that matrix that's left over after you delete the last n minus k columns and the last n minus k rows. Guys, I'm sorry, but you need to remember this now. Right now, you're deleting the last n minus k columns and the last n minus k rows. Next week, when we do optimization and we work with the bordered Hessian matrices, you would have to delete any n minus k columns and any n minus k rows. But right now, it's the last n minus k columns and the last n minus k rows. So what in God's name does that mean? Take a 3 by 3 matrix, n is equal to 3. Let k be equal to 1. K has to go from 1, 2, all the way to 3. I need to find out the determinant of the matrix formed by deleting the last n minus k columns in same rows. N is 3. K right now is equal to 1. So I need to delete the last two columns and the last two rows. Goodbye columns, goodbye rows. I'm left with exactly this thing right here. And the determinant, not the absolute value, the determinant of this thing would then be your first order leading principal minor. Now I need to delete the last n minus k 3 minus 2 columns. So last column, last row. the determinant of this thing is my second order leading principal minor. And finally, I need to delete the last n minus k, 3 minus 3, 0 columns, 0 rows, nothing to delete. So that's your last third order leading principal minor. But leading principal minors are not the same as principal minors. That's why I cross that term out there to make sure that you get the difference. What are principal minors? Principal minors now say is the determinant of the matrix left over by deleting quote unquote any n minus k columns and the same n minus k rows. Okay, so let's do it this way. Someone gives you a 3 by 3 matrix. You now let k be equal to 1. Give me the determinants of all matrices found by deleting any two columns and the corresponding rows. So here I can delete the second and third columns, second, third rows. I can delete the first, third columns and first, third rows, or I can delete the first, second columns and first, second rows. What's left over are the determinants of those creatures are your first order principal minors. I apologize for the notation. All D1s refer to the same thing. They're all first order principal minors, but there are 3 of those over here. By the same token, there are, in this particular example, there are 3 second order principal minors, the determinants of these 3 matrices found by deleting any one column and row. And in this case, there's only one third order principal minor found by deleting 0 columns and 0 rows. So you'll notice that these principal minors, right? So this principal minor is also a leading principal minor. Agree? That's not a leading principal minor, simply a principal minor. You notice that this principal minor is also a leading principal minor, but not that one, not this one. And this principal minor is also a leading principal minor. So this is an example. 3 by 3 matrix, leading principal minors. Easiest way that I would highly recommend that you remember this is by imagining the first 1 by 1, 2 by 2, 3 by 3. See 1, 1 by 1, 2 by 2, 3 by 3. Take the determinants of those things. Those are your leading principal minors. Principal minors, the first order ones are simply the diagonal elements. 1, 2, 3. So here's your 3, minus 1, and then your 2. The second order ones are more tricky, so they're all 2 by 2 matrices that you can form. So you can take this 2 by 2, you can take that 2 by 2, you can take that 2 by 2. They're all listed over here. And finally, of course, you have the 3 by 3. There's only one 3 by 3, and then we're done. So leading principal minors, we understand that some leading principal minors are principal minors, but not all principal minors are leading principal minors. Oh, Jesus. Okay. Quadratic forms. Extremely important topic. Not. Uh, anyway, let's talk. A quadratic form, if you remember, let's go back. If you remember high school, the quadratic formula, it was used for ax squared plus bx plus c is equal to 0. So the word quadratic means that there are square terms inside. But the problem now is that you could actually have, so whatever equation you have has a bunch of squares and cross terms. So for example, you could have a quadratic form in 2 variables. 2 variables means x1s and x2. Here's an example. You can see there's squares in x1, there's squares of x2, and there are cross terms, right, in terms of x1, x2. I have purposely not uh, brought these 2 terms together. I've left them separately. I'll tell you why I do this on purpose. You should be able to take this line of algebra right here and write as a vector matrix vector form like this. So I urge you to convince yourself that this thing will give you that thing. And if you take a close look at this, this is not a symmetric matrix. In fact, it's asymmetric. Right? What you would have to remember going forward, anytime somebody gives you a quadratic form, no matter what you do, right? Just like you have to check your Instagram before when you wake up in the morning and sleep at night. No matter what you do, when you do quadratic forms, the middle matrix always has to be symmetric. You can't forget that. So To make it symmetric, I'll show you a trick. Symmetric means that is as follows. You notice that this 2 is corresponds to x1 squared is that one right there. The minus 3 for x squared is one down there. So what's this 4? Well, this 4 must refer to this 4 for cross terms x1, x2, and that minus 6 is corresponding to this cross terms x1, x2. So if you want to make these things symmetric, right, the same, you would first have to gather these terms together, which collectively becomes minus 2x1, x2. But now to make it symmetric, you have to split them up, right? So minus 2 divided by 2 would give you minus 1 and 1. So if you wrote it this way, so knowing that this is 2x1 squared, here's your 2, minus 3x2 squared, that's your minus 3. Knowing this is minus 2, and that you have to make a symmetric matrix, you would have to divide this number by 2, and that gives you minus 1 and minus 1. Now we have a symmetric middle matrix right here. And you should always, always, always do that. Some examples. In these examples, I've purposely expressed the first expression in a way that ensures that this middle matrix is symmetrical, right? You can see here's your A for x1 squared, there's your A. Here's your C for x2 squared, there's your C. Here's a 2B, and inside the matrix I have to then take this number divided by 2, there'll be a B and a B. Again, by the same logic, if there's a B here, I did this on purpose by the way, right? To put it on the middle matrix, I would have divided by 2. So here's your B2, B2, B divided by 2, B divided by 2. And now, again, I do this on purpose. If I see this as the middle term, on the matrix, I would have to take middle term divided by 2. That's that term divided by 2, term divided by 2. Again, showing you how to write this very quickly. And we're ensuring that the middle matrix is always symmetrical. In general, though, you could actually have more than one x1, x2. You could have x1, x2, x3. So you would have terms in x1 squared, x2 squared, x3 squared. Then you would have cross terms in x1, x2, x1, x3, x2, x3. So such larger quadratic forms involving many x's, n x's, Nancy x's, is given by this monstrous expression. I'm not even going to go there right now, sorry. But you should. So you could do it this way, you could do it this way, you could do it this way. One way to know what in God's name is going on is choose a number for n. Obviously not 2 because 2 is too easy. How about you choose 4? And ask yourself, if I had 4 x's, x1, x2, x3, x3, x4, what would the squares and cross terms look like? Try doing it this way, try doing it this way, try doing it that way. And that will once and for all reinforce these mathematics and these kind of computations. This is very important for MFE students. You'll be doing these kind of summations with all kinds of these things, manipulations going around in Angela's class. So you better practice now, right? So I can express a quadratic form this way. So you can see here's the x1, and these are all the terms that you see over here, right? And that allows me to write down this matrix like this. So right now, I have not ensured that the cross terms x1, x2, x1, x3, and so forth are going to be giving me a symmetrical matrix. So as I've written right now, this is in the form x transpose a matrix B, right? Big B, consisting of baby B's times the vector x. But baby B's, this is not a symmetric matrix. B1n is not the same as Bn1. But you know what to do, right? What should you do? Quickly. How do I make it symmetric? Well, I gave you the hint in the previous slide. If you want to make it symmetric, you would have to then, of course, add them up and divide by 2. So what you would do is, you would add up B1n, Bn1, divide by 2. So this would now be your, instead of having B1n here, you would have B1n plus Bn1 divided by 2. And here you would also have B1n plus Bn1 divided by 2. Okay? Incidentally, you're now in a very strong position now that once you have a symmetric matrix A, and you now know that matrices represent linear vector functions, you now know what precise linear vector function a symmetric matrix is representing, right? Like quadratic, right? So just to make sure that we get this, let's do an example. So you have a 3 variable example. See, there's x1s, x2s, x3s. Okay. Bunch of x term, cross terms, squares, all this stuff. If I left it as it is and wrote it in this form, notice how the B matrix is not symmetric. But now I start to say, wait a second, how could I make this symmetric? Again, I remind myself that this 3 up here is for x1 squared. That minus 1 would be the coefficient for x2 squared, and that 2 is the coefficient of x3 squared. So these are the diagonal elements are the coefficients of x1 squared, x2 squared, x3 squared. This one, as you can imagine, is, since it's row 1, column 2, has something to do with x1, 2, right? So you can see the cross product x1, 2 has a coefficient 3. And since this one is row 2, column 1, must be the coefficient of cross terms x2 times x1, c minus 1. So that 3 must be for x1, x3, and that 1 must be for x3, x1. This 2 must be for x2, x3, and that 4 must be for x3, x2. And of course, if I collect these terms, then I remember that I have to divide by 2, so that you now have you'll keep the 3 minus 1 2s. 3 minus 1 2s are the squared coefficients, so those stay. But now this 2 gets divided by 2, 1 1. This 4 gets divided by 2, 2 2. This 6 gets divided by 2, 3 3. But you could have gone from here to here without writing these expressions down. What would you have done? You would have kept the 3 minus the diagonal terms, right? But here you could have gone much faster. 3 plus minus 1 is 2. 2 divided by 2 is 1. 1, 1. 3 plus 1 is 4. 4 divided by 2 is 2. 2, 2. 2 plus 4 is 6. 6 divided by 2 is 3. 3, 3. So you don't necessarily have to do this hideous math. You can go from here to here by just doing what I just told you. Now comes something extremely important. There's this notion of how to sign a quadratic form, which some books call putting a sign on a matrix A, right? Because quadratic forms are x transpose A, x. If you get this intuition, this will make your life incredibly easy, especially when you do proofs. You really, once you get this, you're done. Take a look at this quadratic form. Okay? Notice how the matrix is symmetric. If I went to Wolfram Alpha, which I did, and I were to plot this thing in 3 dimensions, it would look like this. And if you take a very close look at this, you will notice that at the point 0, 0, the value of this quadratic would be equal to 0, right? Because if x1 is 0, x2 is 0, everything then becomes 0. So except the point 0, 0, at any other choice of x1, x2, it doesn't matter whether in the first quadrant, second quadrant, third quadrant, fourth quadrant, the value of this expression will always be positive. And that means that the surface is always going to be floating above the xy plane. Got it? This one, in some places, this surface, this equation, touches the xy plane. In other places, it floats above the xy plane, but it is never ever below the xy plane. Here, the surface is always, except at point 0, 0, below the plane. Right? And this one, it is below or touches the xy plane, but never is above the plane. So there are surfaces that in some intuitive sense take on always with the number q, always takes on values which are strictly positive, except at the location 0, 0. There are other surfaces that where the value of q is bigger than equal to 0 for all values of x. There are quadratics out there with the value of q is always negative except at the point 0, 0. And there are surfaces where the quadratic is less than or equal to 0 for all values of x. So you will notice that if you're paying attention, here I was very specific to say it's always positive except at the value 0, 0. It's always negative except at value 0, 0. But here I said it's bigger than or equal to 0 for all values of x and less than or equal to 0 for all values of x. Keep that in mind. There are other surfaces, your classic good old textbook undergraduate saddle point, where the surface lies both above and below the xy plane. Right? So you have all these interesting possibilities. floating above the xy plane except the point 0, 0, below the xy plane except at 0, 0. Either above or at the plane, either below or at the plane, or sometimes above, sometimes below. In mathematics, these are these graphical things that you see here are given very specific meanings. Whenever the value of q is always positive except at the point 0, 0, that quadratic or the matrix A is called positive definite. Okay. If I can jump ahead, what that means is here's a surface which is always above the xy plane except the point 0, 0, which means give me any value of x1, x2 other than 0, 0, and the value of q will always be positive. This is exactly what you see here. So if the value of q is always positive, i.e. this surface is floating above the plane except the point 0, 0, we say that quadratic has positive definite, or the matrix has positive definite, PD. If it is bigger than or equal to 0, and I'll jump to the next slide, that's right here. So the surface never is below the xy plane. It either touches it or is above. That means the values of q are either bigger than or equal to 0. If that's the case, we say, and notice instead of saying, now say if the q is bigger than or equal to 0 for all values of x, we say that the quadratic or the matrix is positive semi-definite, PSD. If the quadratic is always negative, except at the point 0, 0, we say it's negative definite. If it's always less than or equal to 0, for all values of x, it's negative semi-definite. And if it is none of these, we call it indefinite. So you'll notice that the reason I insist on putting this clause in here, except at the point 0, 0, when I talk about positive definite and negative definite, is because why? Why do you think I said that? Why do I have to put this here but not here? It's because if x was 0, q will always be equal to 0. So for any of these things at 0, 0, these q's will be 0. So if I'm going to talk about a q being positive, I have to talk about all values of x1, x2 other than 0, 0. That's why you specifically said other than 0, 0 here, other than 0, 0 here. But since this allows the possibility of q being bigger than or equal to 0, I don't have to say except for the point 0, 0. I can say for all x's. Same thing here, all x's, right? And by the way, PD is the analog of greater than inequality. PSD is the analog of greater than or equal to inequality. ND is the analog of less than inequality, strong. And NSD, of course, is the analog of weak or less than or equal to inequality. So it shouldn't be surprising that if something is positive definite, it must be positive semi-definite, but not necessarily the other way around. If you're negative definite, it must be negative semi-definite, but not necessarily the other way around. So again, pictures. Here's a positive definite. It's the q is always positive except 0, 0. Negative definite, the q is always negative except 0, 0. Positive semi-definite, the q is bigger than or equal to 0. Negative semi-definite, the q is always less than or equal to 0. And now you have indefinite. Sometimes the q is positive, sometimes the q is negative, etc., etc. Now comes, well, how do we know a matrix, a quadratic is PD, PSD, ND, NSD, indefinite? Let's do a bunch of proofs. We're doing this on purpose because you have to be able to do proofs in graduate school. So we want to understand how to tell whether a matrix A or the quadratic is PD, and etc., etc. I'm going to do proofs of the type that P implies if and only if. So you have to go two ways. You have to show that if P, then Q, and if Q, then P. What I mean by this is, and for your convenience, I've done this, something like this. Take a look at the first two lines here. I first ask, what do I need to say about A, B, C so that A is positive definite? That's P, the arrow going in this direction. But now the arrow can go in the left direction. And ask the reverse question. Instead of asking, what do I have to say about A, B, C so that the matrix A is positive definite, you can ask the reverse question. If you knew A was positive definite, what then must be true about A, B, C? So the proofs are going both ways, this way and that way. The fact that I've actually highlighted this means that this proof comes next. And I'm going to follow Martin Osborne's uh, methods because his is more elegant than most textbooks. And again, it gives you an example of how, what, remember that I believe Colin Stewart is going to teach micro. He's a former student of Martin Osborne. So both of them use very precise language and a very interesting way of thinking. Let's start then. What do I need to say about A, B, and C so that this quadratic will be strictly positive for all values of x1, x2 except 0, 0? Well, I have to say something about A, I have to say something about B, I have to say something about C. Where do I begin? Let's start with A. And what Martin Osborne says is, okay, well, A could be any number, it could be 0, it could be not 0. Let's see what happens if it is 0. What will actually, so suppose, is it possible for this quadratic to be positive for all values of x1, x2 except 0, 0, if, for example, A was 0? Well, if A is 0, the quadratic becomes this. Now, what you want to know is, here's what Martin does. Very clever trick. I thought it was kind of clever. He, he has said, okay, well, A is 0. He doesn't bother talking about B's and C's. What he does is he says, wait a second. You want to know if, is it true whether A is equal to 0? Is it even possible that this quadratic is strictly positive? If I can find one violation, then I know there's no way A0 will work. Well, you have found a violation because let's try evaluating this quadratic at the point x1 is equal to 1, x2 is 0. When you stick it in, 1 times 0 becomes 0. This is 0. The whole thing becomes 0. So that means you've just shown a very elegant example. You're looking for values of a, b, c so that the quadratic would be positive definite, strictly positive. You start by saying, let's pretend a is equal to 0. And by playing, you didn't even know what the value of b and c was. You simply evaluate the quadratic at some location, x1, 1, x2, 0, and found that no matter what b and c are, the value of the quadratic is going to be 0. So what you've shown is, if a is equal to 0, there exists at least some point out there other than 0 where the quadratic is 0, which is not what you want. Therefore, if you want the quadratic to be strictly positive, you need the number a to be not 0. So, for sure we know a must be a number other than 0. It could be now positive or negative. Which one is it? Let's do it this way. Here's the quadratic. We add this term and subtract this term. Nothing changes because the whole thing adds up to 0. You should collect these expressions, right? Do this way before the test and show that you can go from here to here and here. So what you've done is you've broken this up into two parts, a first term and a second term. Before I go on, notice you have the parameter a, which right now could be any number other than 0. Well, it should be a number other than 0, into something that's square plus something but into squares. Okay. So notice that if I ultimately want this q to be positive, since this is a square, squares can be bigger than or equal to 0. They cannot be negative, right? So somewhere, doesn't matter what value of x1, x2 I choose, doesn't matter what value of b and a I choose, this square right here is always going to be bigger than or equal to 0 for the time being. That means that ultimately, if I want this whole q to be bigger than 0, this baby a is a number that cannot be negative. We also know it can't be 0, right? Because we can't be 0 from the previous slide, so it has to be positive, right? So we have to assume that a is positive. It doesn't guarantee that q will be positive, but if you want q to be positive, you have to have a as a necessary condition being positive. So going forward, we assume a is positive. Now let's do some interesting analysis. What happens if x2 is 0? Why do I have to say x1 is not equal to 0 at the same time? Because remember, you're trying to find out the value of q for all values of x1, x2 other than 0, 0. So if one of them is 0, the other one cannot be 0 for you to establish what happens to q. So if you say x2 is 0, you then also have to assume that x1 is not 0. So what's going to happen? If x2 is 0, This thing goes to 0 in the first term. X1 is not 0. Something that's not 0 squared becomes positive. But you also said A was positive, so the first term has to be positive. It's not bigger than equal to 0. Plus, second term. You said x2 was 0. Well, x2 is 0, so 0. So now you're positive, and a 0 gives you positive. So right now, things are looking good. So having a positive momentarily for those values of x1s and x2s gives you a positive definite quadratic. What happens when x1 is 0? I can't simultaneously have x2 be 0 at the same time if I want to find out when q is positive. Well, if x1 is 0, this goes to 0. No matter what b, a, and x2 are, this will be a square, positive. A is already positive. First term has to be positive. Plus ac minus b squared. I don't know anything about this right now. I do know a is positive, and I do know that anything squared is positive. Remember that x2 was not 0. So you know this has to be positive, right? Because you said it's not 0. I want the whole sum to be 0, to be positive. Positive plus a positive. So I just need to actually have this thing be positive. And for this thing to be positive, I need AC minus B squared to be strictly bigger than 0. When x2 is not equal to 0, and just by sheer coincidence, x1 is equal to minus BA over x2, this thing becomes 0. That thing will then be then again, by the same logic I just used earlier, just now, you can deduce that again AC minus B squared must be positive. And again, of course, if take any point where x2 is not 0, right? And x1 is not equal to minus b a x2, the first term has to be positive. Everything is right positive, and the second term will be positive, provided ac minus b squared is positive. So what you need is a to be positive. You need ac minus b squared to be positive. These two things are going to for sure guarantee that q is positive. And by the way, many textbooks say c must be positive, but you don't really need that as a condition. It's just a implication of these two equations. So saying a is bigger than 0 and saying ac minus b squared is bigger than 0 implies that c is bigger than 0. It is not a requirement. Nowhere over here did I want c to be bigger than 0, right? So it was just an aside, an implication. Right? What about the other way around? Someone tells us that a is positive definite. What then must be true about ABC? And if we find the exact same results that we did a few seconds ago, we're golden. We are given a quadratic. We are told this expression is 100% strictly positive. Now, what Martin does is he says, okay, fine. If it's strictly positive, then for all values of x1, x2, other than of course 0, 0, this must be positive. So he can start to play around with this, and he can fool the system to spit out just the values of a's and b's and so forth, right? Because in what sense? So here's what I mean. He says, look, you know this expression is positive everywhere, including obviously at x1 is 1, x2 is 0. If you evaluate the quadratic at 1, 0, you notice it exactly equals to a. Now I know that q is positive. If q is positive, a must also be strictly positive. So that's the exact same result that we got earlier. Knowing that q is positive must mean that qa is positive. Now he wants to, what he's doing is make a dirty trick. He knows that he has to derive these conditions, right? Give back. It'll be kind of nice. So he's already gotten a is positive. He just has to get this thing right here. So what he has to do is he has to choose the x1 coordinate and x2 coordinate in such a clever way that when he sticks it into this equation right here, out comes ac minus b squared somewhere, right? So by choosing minus ba for x1 and 1 for x2, you can see by doing this, the first term goes away, right? This then becomes a 1, and now you get ac minus b squared divided by a. You know this thing has to be positive because you're told that q is positive. The denominator is positive, which means the numerator must also be positive. So you get back exactly the same results that you got initially. And by the way, again, it's an implication of these two equations that c must be positive. We summarize. Having done the if and only if proof, we can now state this thing here. So if you have this quadratic form, the only way the matrix can be positive definite, representing a function that's always floating above this xy plane, except at 0, 0, is if a is positive, ac minus b squared is strictly positive, and by the way, c will end up being positive. Now we do the same thing for PSD. All right, so we now want to know what should be true about A, B, C so that Q will be bigger than or equal to 0. By the exact same logic that I did earlier, I now ask, is it possible? What must be? Is it possible that Q is bigger than or equal to 0 when A is equal to 0? Let's see. Let A be equal to 0. That's what happens in the quadratic. And again, what we're using modern argument logic, modern osmosis logic. He says, look, you want Q to be, you have A is equal to 0, and you wonder if that's going to make sure that Q is bigger than or equal to 0 everywhere. Well, if that's true, let's say Q should be bigger than or equal to 0, and let's say at any point x1, any value for x1, and in particular x2 is equal to 1. He does this because if you leave, you want to say something with b's and c's, right? If you make x1 any value it can take x2 and make it 1. If x2 make it equal to 1, then you ask yourself, wait a second, with a is equal to 0, when will this expression be bigger than or equal to 0? Positive, semi-definite. Well, since x1 can be a number that's positive, minus, or 0, you want this thing to somehow go away. That requires setting b is equal to 0. And if you want the whole q to be bigger than or equal to 0, you need c to be bigger than or equal to 0. So what you've done is, if a is equal to 0, for sure you need b is equal to 0, and you also need c to be bigger than or equal to 0. And by the way, under those conditions, ac minus b squared is going to be equal to 0, right? Because a is 0, b is 0. Sounds good? This is a bit more subtle. Now you needed c to be bigger than or equal to 0. Previously, in the previous proof, c was positive just as an implication of the two equations. Now you need c to be bigger than or equal to 0 for this to work. So what about a? So now you know what b and c must be when a is 0. What happens when a is not 0? Again, the same first term, second terms. And again, by the same logic I used earlier, if you want this thing to be bigger than or equal to 0, ultimately, you need to make sure that at the very least, a has to be a number bigger than or equal to 0, right? It cannot be negative, right? So it has to be a number bigger than or equal to 0. Why do I say bigger than or equal to 0 and not bigger than 0? Because the previous slide shows that it's a0 works. You can, in fact, find values of b and c with a is equal to 0 that make sure this is positive, semi-definite. So we start now with a being bigger than or equal to 0. And now we start. Let's imagine that x2 is equal to 0, and now consider any values of x1. Well, if x2 is equal to 0, and now you have any value of x1, this first term is going to be a number that's bigger than or equal to 0, right? Because a is bigger than or equal to 0, and now you're squaring something which could be bigger than or equal to 0. Plus, since x2 is 0, this is 0. Now let's imagine x1 is 0, but take any value of x2. Well, then again, the first term is going to be bigger than or equal to 0. And the second term now is a bit more tricky. Since you have any value of x2, any value of x squared is a number bigger than or equal to 0. A is a number that's already known to be bigger than or equal to 0. And now you want the entire sum to be bigger than or equal to 0, right? To do that, you need the first term to be bigger than or equal to 0. You need the second term to be bigger than or equal to 0. Since you're dividing by something that's bigger than or equal to 0, you have to make sure that the top is also bigger than or equal to 0. So therefore, it implies that you must have ac minus b squared bigger than or equal to 0. Sorry, excuse me. When x2 is not 0, and x1 just so happens to be equal to that creature inside, then what happens is the first term becomes 0. Second term, exact same logic as the previous line, again, same implication. And again, when x2 is not 0, and x1 is not equal to this value right here, this term has no choice but to be bigger than or equal to 0. Actually, just realized I didn't have to do this, but anyway. Plus, and this second term again, but the same logic as before, implies that ac minus b squared has to be equal to 0. So these are the conditions you need. So you need, if a were positive bigger than or equal to 0, and c were bigger than or equal to 0, and ac minus b squared would be bigger than or equal to 0, it would mean that q is bigger than or equal to 0. Let's have the proof go backwards. You're told that a quadratic form is positive semi-definite for sure, what must be true about A, B, C? Can you say something about these things? Since I know this expression is bigger than equal to 0 everywhere, let's pick some points. Well, Martin picks some points. He picks 1 and 0. You already know why. Because when you pick 1 and 0, you notice that Q is equal to A. Since Q is bigger than equal to 0, A must also be bigger than equal to 0. Same result that we got back previously. Now, again, dirty tricks are being played. He also needs to somehow insert values of x1, x2, so he can get some conditions about baby C. So notice how it's very clever. He now chooses x1 is equal to 0, x2 is equal to 1, because by doing so, the only thing that spits out is the value of C. You want to make sure that you can show this, okay? And therefore, since Q is bigger than equal to 0, C must also be bigger than equal to 0. And finally, again, he now somehow needs to show that AC minus B squared thing. So he cleverly chooses the location of x1, x2 in such a way that when you stick it in, you get this expression. You already know that A is bigger than equal to 0. You know that this entire thing must be bigger than equal to 0. Since the entire thing must be bigger than equal to 0, A is bigger than equal to 0, AC minus B squared must be bigger than equal to 0. So we have done now if and only if proofs. Both things work. At this point, I wonder if I should be reading out the proofs. I think maybe I should leave these as an exercise. Maybe you can actually, yeah. Why don't we actually do that? Since I've done one, the PD and PSD. Why don't you do ND going one way, right? Then ND going the other way, finishing up, and then now doing NSD going one way and NSD going the other way, right? And now this gives you a complete summary of what we've done. And now we're ready to go somewhere. We want to know when would a surface quote unquote be floating above the xy plane except at 0, 0, etc., etc. That boils down to right these conditions right here. So you want to know under what circumstances Q will be PD, PSD, and ND, NSD. You know the restrictions of these parameters, but how can I use them in practice? What do I need to do can I come up with an algorithm that I can use on this matrix to tell me whether these parameters, which of these conditions have been satisfied? Here it comes. Slowly. You remember that here's a quadratic form. We have done leading principal minors. So you remember that the leading principal minors of this 2 by 2 matrix, remember it's a symmetric matrix, okay? It's not A, B, C, D, it's A, B, B, C. You know the leading principal minors are A, the determinant of A, and of course A, B, B, C. You also know the principal minors are A, C, the diagonal terms, and then of course the determinant of the entire matrix, which is AC minus B squared. Beautiful. Now you remember that these are the conditions for PD, PSD, ND, NSD. Take a good look at this. If it's PD, A must be strictly positive. That means this leading principal minor must be strictly positive, and AC minus B squared must be strictly positive, which means this leading principal minor must also be strictly positive, and then you're done, right? So all you really need is if the two leading principal minors are strictly positive, then what happens is you know that this matrix represents something that's I was going to say professionally developed, but no, positive, definite. But you remember from undergrad something about looking at diagonal terms, being positive, negative, and all that stuff. Well, that comes from the fact that what you really actually need for PD is A to be bigger than 0, leading principal minor. AC minus B squared should be positive. Second leading principal minor should be positive. Those are the only things you need. But since you know that these two equations also imply that C is positive, then practice what people do is they know that A has to be positive, and if you don't want to compute AC minus B squared and then find out it's not PD, what you could do is you could eyeball and say, wait a second, if it's going to be PD, I know that A has to be positive and C has to be positive. So a rule of thumb is when going down, in the future, if somebody ever says to you, listen, is this matrix PD? you could quickly eyeball and see, are the diagonal terms strictly positive? They have to be, right? And once they are, then you carry out the initial check of seeing AC minus B squared is positive. Is PSD if and only if, all the principal minors are bigger than or equal to 0. So notice I did not say leading principal minors, but principal minors. What about ND? ND is a bit tricky. The first leading principal minor must be negative. The second leading principal minor should be positive. First one is odd, right? First leading principal minor is an odd number, negative. Second leading principal minor is an even number, should be positive. So for an ND matrix, the leading principal minors must alternate in sign. The first one should be negative, second leading principal minor should be positive, third leading principal minor should be negative, and so forth. For it to be NSD, notice how the first order principal minors, which are these right here, A's and C's, the first order principal minors must be less than or equal to 0. Second order principal minors must be bigger than or equal to 0. So for a matrix to be NSD, the first order principal minus must be less than or equal to 0. Second order principal minus must be bigger than or equal to 0. Third order must be less than or equal to 0. Fourth must be equal to 0. So you can see again the flip flop. And we can now summarize this by this table. I would spend some time getting to know this table, right? So I have now summarized, I've taken the 2 by 2 example in the previous slide, and I have now, again, I remind you the definitions of PD, SD, all that stuff. I mean, PD, PSD, ND, NSD. These are the 2 by 2 conditions. And now I related them to the principal minors and so forth. So let's summarize slowly. A matrix is positive definite if and only if all leading principal minors are strictly positive. These are the determinants of those matrices we form. A matrix is positive semi-definite if and only if all principal minors are bigger than or equal to 0. It's negative definite if and only if all leading principal minors obey the sign. What this means in plain English is the all odd numbered leading principal minors must be negative, all even number leading principal minors must be positive. And now when it's been negative semi-definite, when all odd numbered principal minors are negative and all even numbered principal minors are positive. And if any of these conditions fail, you would have a indefinite matrix. Here's some examples. You should now obviously check. So right off the bat, I can see this may be negative definite. Right off the bat, I can see this will never be positive definite, nor will it be negative definite, right? Because by the same logic I used, you would eyeball those diagonal terms. So why don't you do this? It's also in the homework. Here's how you do it in Wolfram. In Wolfram, by the way, the commands are really weird. You actually have to write down the matrix and ask Wolfram, dear Wolfram, is this matrix positive definite? It may say no. In that case, it may be so. So it, it would not be positive semi-definite then, right? Because any PD is PSD. But had you started by saying, is this matrix positive semi-definite? And it said no, it may still be. Let's see. So you could have a. Let me get this right. So you could have a PD. Every PD is PSD, but not every PSD is PD, right? So that's right. So you could ask, is negative definite, right? You have to say, is it negative semi-definite, and is the matrix indefinite? So practice those. Thank you very much. Take care.